Welcome everyone to our monthly Quantum BC seminar series. Today I'd like to welcome Jinyang Li. He's
Yeah.
going to be speaking today, and the topic is the neural operator learning in quantum simulations. Jinyang is both a junior research associate and a student trainee at the Division of Fundamental Mathematical Science, RIKEN Center for Interdisciplinary Theoretical and Mathematical Sciences, or IBEMS. His research aligns with quantum computing and machine learning, and he has experience in optical quantum sensors and QCD thermal history. Without further ado, please welcome Jinyang.
Yes, I want to also introduce KK. I wrote here as my previous affiliation. I'm a student there. I recognize the universe. Yes, sorry, university. Yeah. Maybe that. Yeah. Then maybe I can start my talk now.
Great. Thank you so much. Yes, please.
Yeah. Good afternoon, everyone. Uh, yeah. So I will try to discuss how to use very tropic models like for example machine learning to study quantum from let's say the data from quantum computer. That's because usually from quantum computer the signal we get is very limited, which means like for time series signals we can only get signals in very limited steps. So if we want get some physics quantity which depends on long-term data. We have to first train the data and predict the long-term behavior. Uh, and our method try to use neural network to predict that. So before everything, I want to show this slide, like why we need quantum computer. I'm not sure most of them are familiar with the way of we doing path integral. Basically, path integral is just the propagation amplitude. And so, as you see, like everything in quantum mechanics and everything that we can describe word in the standard model. And also, if you want to consider quantum causality, you have to write in a quantum formula. And also, from this kind of point of view, everything we can consider is quantum. So that's not special. We want to use quantum computer to calculate everything. And everything I mean, all the physical quantity that we can measure is like such a propagation amplitude. Uh, yeah. So how does kind of such a quantum computer works? Uh, it's quantum computer you can imagine is a more general bits we call the qubits, and this is the very naive quantum spin states we describe in a sphere. And as you see, like classically, we only have like two sides of a bit, but quantum you can have superposition and a lot more. And you know there's also phase phase factor in the quantum, so you can also use the property of interference or something like resonance in the calculation makes we when we do the calculation on quantum hardware we have a more kind of more free to to make our algorithm closer to the hardware. So here I want to show like what is quantum bits. Like we just expand to add into two bases, and for any quantum bits after taking out one like this gamma factor, you have only effectively 2 degree of freedom. And this is our notation to write a multi-qubits. Like you just write this product as a cat form. Hmm. Yeah. What is the like hardware doing? Like in mathematically, all the things in quantum mechanics is described by unitary evolution. So in the quantum hardware, it's like you prepare states with the qubit states as I just mentioned, and you want to operate some unitary, as I showed here. some unitary to evolve your states. And for any of the states after, for NQB state, you can always rewrite into as if it's a digital number, and you just sum over all the possible states with a given coefficient, and then that's a complete description of any state. And you want to describe the such evolution on such states and build some let's say unitary operator by hand. So to build such an operator, we need such very elementary puzzles, elementary parts, and we call that qubit gates. Here, as there's a approximate universality theorem means for any kind of qubit, any kind of unit operator, we can use a set of single gates to approximate the operator in any level of accuracy. This is like very restricted mathematical proof, but in actual we can use a bit more like elementary operation in the quantum computer so that the universal theorem is a subset of our protocol. So here I just introduce some common quantum gates we can apply easily on the quantum computer. For example, there are identity gates and some the poly gates, and all of them can give you a rotation because what we do is like exponential I to the this kind of operator. So it's give you a matrix rotation on the real quantum computer. And also to make it complete, we also need like S gate, T gate, and a Hadamard gate. As you see, like S and T, T is just the square root of S, so we are not just considering the most elementary part, just those we can do on a quantum computer. And also this Hadamard gate gives you the entanglement, and S and T give you the phase interference, something like that. And to here before here I saw like a single gates, but that's not enough because if we want like consider any kind of your on operator, we have to somehow connect different qubits. Connect the interaction of the different qubits. So here the most general way is use this kind of C0 gate, and also this thing I don't know if this gate is very necessary, but anyway, with those two, it's complete so that you can connect to different qubits. And here's the example, like how do we how do we construct a special gate like the Bell state? You start from the 0, 0 and use Hadamard and not gate. Just do straightforward calculation, you get that's a Bell state. So that once you trace out one of the operator, that's not the pure state anymore. Means two states are entangled. So with the help of such gates on the two qubits, we can produce those states cannot be produced by one qubit gate.
Jinyang, I'm so
So
sorry to interrupt. I just wanted to clarify if you were planning to share your slides. Um, are you, we can't see them right now. I just wanted to make sure you weren't sharing them, or if you were wanting them to be shared, we don't see them.
No, I can see the slides.
You can?
I can.
You can't. Yeah.
No, I can.
Oh,
We
you
are seeing
can.
the slides as a view.
Okay, interesting.
uh,
Other people, so is it just me then?
so should I reopen
Maybe
it?
it's just me. That is strange if I'm not seeing them.
Mm-hmm.
Okay, well, if, yeah, other people are confirming they can see them. So I'm so glad, and I'm sorry that I interrupted.
Oh, no
Yeah,
And
problem.
it must
no
be just
problem.
a problem on my end then.
Mm.
Please go on.
Yeah. Okay. Thanks. And yeah, and here we just talk about all the possible single gates. So for any kind of quantum like protocol or algorithm, finally we are doing a thing showing unit space. Like on the left, we prepare the initial states, and you put a lot of single single gates on your whole circuit and run that from the left to the right. And finally, you do some measurement on some basis. And quantum computer is just run in this way so that you can get some counts in a statistical way. So now I just give a very brief introduction of what's machine learning. This word is, to be honest, very big. And as I show in the screen graph, like machine learning is just part of AI. And what we generally call machine learning now is actually just deep learning with neural network, because we are using neural network to feed some of the functions. But that's not part. That's just part of machine learning, not all of the stories. And what we are using now in deep learning is like you have a lot of data and you have a model with a lot of parameters, and you want to train those parameters to fit your data set in a way you design. That's what we call deep learning. And there's a figure just showing like how to use this neural network. Like you have some initial some inputs and some internal functions, and you construct very complicated functions and activate by your different data and do tune those parameters step by step, and finally makes the loss goes to zero. Usually loss is defined by the difference of two functions, and when the difference is zero, it means your fitted function is exactly the same with your target function. But usually it's difficult. We just make the loss as small as possible. And typically, like traditionally, there are a lot of different way of designing your neural network. For example, CNN, RNN, those are reflecting, in a physical way, it's reflecting different symmetry because for CNN, it's more like visual thing. Uh, we 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 do the patch kernel step by step, so it's actually reflect the translation symmetry. And RNA is like as you say, the time step is only depend on last step, so it's more like we consider real sequential signal, and we may also think it sometimes can reflect the time translation symmetry because in some other sense it's only consider time and the derivative of time. And there are also some other very popular neural network like graph neural network, equivalent neural networks. And also, I guess the transformer is also very popular now. Just because it's um, it's a bit more complicated. I didn't show it here. And all the neural networks based on such neural universal approximation theorem means any kind of layers, any kind of neural network can fit to any kind of functions. It's just a proof. Like in general, we can do that, but a better design makes this procedure faster and more accurate. So yeah, here just background, and here and those spectroscopy is the main target we are going to talk about. Our work will be go on to some operator learning and uh, to learn the dynamics of any operator in a quantum system, um, and to show that we need a target, and this is our target today. So we call the spectroscopy, and it's essentially just a Fourier mode of a two-point function. And if we write in this way and insert some complete state here, you can see the spectrum is basically just a excite operator. Sorry, use the operator to excite your states and see how much it excite and see the whole spectrum. For example, if we doing in a massive field theory with a single particle excitation, then what we will see is a spectrum of single particle, and n will be different energy eigenstate of this particle, and the lowest one will be the mass of this particle. So uh, this is a more clear picture of how this excitation works. Like you prepare the ground state, and excite first prepare that's the zero state from quantum computer, and we prepare the ground state and excite that. So there are already some excitation, not only the ground state, and because it's the time evolving, it's more like free evolved to some time, and finally do the measurement. We generally believe the signal should be the such kind of periodic because all the function inside is just the sine function and cosine functions. Uh, and there's a very toy model way, like how to measure such like 2-point functions, because we generally believe such 2-point functions are complex. That's not a real number. Means which it's not a number you can directly detect from the quantum computer. So here, one way is to introduce the ancillary qubits. For example, you here give a Hadamard gate on this ancillary zero state, and you just straightforwardly calculate this circuit from left to right, and measure x value and y value, and sum them in a way written here, like use x plus imaginary y, and you get like this is just straightforward calculation. You get the result of this expectation value. It's just the expected value of those 2-point functions. So in general, the just want to say such correlation functions is measurable on quantum computer. Maybe this algorithm is too easy and sometimes too noisy, but of course there are a lot of improvement based on this kind of simple example. But I just want to say this applicable in quantum computer now. And yeah, so our target is try to assume we already have such a signal, so how can we make it better? So the theoretic structure of our work is following. Like uh, for we first write any of the operators into a poly basis, and after writing that, you can see the poly uh, because of the Heisenberg equation, those coefficients will obey like ODE functions, and once it's just the ODE function, like close to the classical word, and a lot of like traditional method can be used. And here we use the very special one called neural ODE. Means you use a ODE, you use a neural network study ODE kernel and to do the long-term prediction. And I will show this result in the final. So let's do that step by step. Uh, for NQB states, let's first expand that. And as I mentioned, after inserting the Heisenberg equation, all the things we do is in the Heisenberg picture. All the time evolution will be insert on the operator, like we just insert U dagger U here, and we will see once the operator time dependent, we can make it the like coefficient time dependent, and those bases are a stationary. It's just those poly bases, and in a way of that, we can write the operator time evolution into the coefficient time evolution, and because the Heisenberg equation is just one derivative, so uh, we can expect uh, such a way to write our final expression of all the coefficients. We don't expect like higher derivative on these equations. So we can believe such derivative of any coefficient is a function of all other coefficients. And and we will use this neural ODE to learn this structure. So here is give you a very good figure to show how those neural ODE works during the training. Like we prepare a sequential data, and and we know the sequential data come from a neural network, so we can design a special dynamics called neural ODE to fit such curve. It's like you given an initial value and tell them uh, the differential kernel, which is represented by the neural network, and train the loss function between the two trajectories. So then the whole trajectory the neural net predict will become the trajectory of the real data. That's the way we build neural ordinary differential equation. And yeah, so finally it's a way like we can like subtract the internal dynamics uh, that we have in the classical data. And the only special things I think here is like we already assume the form of the dynamics is a ODE. We don't really expect that is a higher order or other kind of form. Like we already make our problem simpler and so that neural network already know there's a dynamics inside. It just need to learn what is the dynamics. Sorry. So here I give a three cubic example to like how our protocol works. Like we design a Hamiltonian, like very simple transfer field Ising model, and we know in such a model, uh, single particle excitation is it's written by the like sum of different poly X operators. This can be seen from a free theory. Like if we don't consider any X operator, we only consider the poly Z operator part, then that's a free theory. And we know in such a free theory, such any of X operator is exciting to zero state to one state. So so in such a case, we call that uh, s- uh, the excitation of single particle excitation operator. So it's more like what we did in the field theory. Like in the free theory, you have a single phi to excite a particle. Once we turn on the interaction, for example, in QED, we don't expect the free operator is still, I mean, the single operator is still the one particle one free particle excitation, but we still expect that the form of one particle excitation means it excites um, one particle state, but it's not eigenstate of Hamiltonian or momentum. It's just excite one particle. Uh, and here's our neural network design. Like what the input of the neural network is the a set of coefficients, and it will uh predict the derivative of in a way like I saw in previous page. Like it's only the first order derivative. Yeah, and here is our result. Uh, like uh. the maybe I skip too much, but the left up panel is like the coefficients of any operators. If you still remember the complete base here, I wrote in this way to the we can always write in such complete base and to get really get one of the coefficient inside out, we just need to do a trace on the base we choose. So we just need to trace operator and on like let's say sigma alpha so that we can pick up C alpha. And here I just wrote here like the left up panel is a coefficient prediction of different bases. For example, xz means we pick up the coefficient that correspond to the x, y, z, this poly basis. As you see, maybe the detail, I mean, line to line corresponds maybe not bad, but all the dynamics part, let's say the frequency and also the average of derivative, those things correspond very, very well. And 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 with after like we train on the left the blue region and after train such a operator we can in general construct any kind of operators So here I show how to construct the 2-point functions with those all basis expansion, and the result is also different. Also like only reproduce the dynamic good, but not like every data point good. That's why we also use that to predict some dynamics. And here the bottom line is our target. It's the Fourier expansion of the upper panel, and as you see, the raw signal is the only thing we can get from quantum computer, like the from 0 to 5, because in quantum computer we have only very limited step. We cannot predict more. If we do more, the signal will be completely lost. So the blue is in general we can get from the quantum computer, and we try to use that to analyze what's the energy spectrum, and the exact one is like in theory, theoretically in such toy model we know what's the mass spectrum, and it looks very different. But after with such a prediction, we see those two peak structure, and also the value of the peaks are very close to the real the exact number. So that's basically the first goal of our research. But the problem here is such algorithm is not scalable. Means for such a basis, for n qubits, we need 4 to n basis to expand any operator in a complete way. So somehow we need to make it simpler to reduce the number of our bases. Here we use the very physical way to truncate that, so make our protocol scalable. Uh, I call the physical truncation because we just utilize the locality in such spin model. So we generally believe such 2-point functions will decay along with the distance. So for final signal, we are interested. We don't really need care about those operator, not in the nearest shape. Means for final basis, we only consider the coefficient in front of the nearest basis. That's enough. And for such operator, the first one is identity operator. So that's the nearest, and another is a single poly operators, means in each of the spin, we have a 3 poly operator, I mean x, y, z. So those two, though this is also local, and the nearest is like we only consider the single operator nearby of 2 qubits, so that we have like n minus 1 different nearby 2 qubits, and each of them have 9 gates. That's all. Because beyond that, we will have a uh, like this kind of exponential. For example, if we consider xiy, that xiy is xiy operator, and we will have a exponential minus m times 1 here. But if it's longer, it will be longer. This number will be bigger, so we just truncate up to this level. Uh, yeah, so after truncation, the neuron the shape of the target function is also changed, because previously all the information is already in the coefficients, but after the truncation we lost some of those information. It's more like we enforce the neural network to reproduce such information with very limited input, and those information is kind of time dependent, and um, and mathematically, we know there's a solution. Like for such truncated operators, it'll be such a solution. Maybe it looks a bit ugly, and those C1 to the CNO nearest is our input, and the rest is just the internal parameters of this function. And so we know there's a exact solution. It's just in this shape, in that shape. So and you can just write the t explicitly here. So and because of the task is getting harder to if we want neural networks still reproduce signal, we have to make a very specific neural network design so that it can capture the signal we want better. So here we introduce the time bending. I personally think this is very technical and already well applied in industrial. For example, for the large language model, actually there are a lot of such time sequential bending. And here in the and I mean we call the middle layer, hidden layer called latent layer, and there are a lot of like kind of embedding different information in the hidden layers. And here we just choose the sine and cosine function so that the neural network can capture those frequency signal better. Just as we said before, this is designed for detect to two-point functions, and those two-point functions, we generally believe that two-point functions yeah, can written in sine and cosine functions. And this is the C of t, like with or without truncation. And as you see, the difference is not so big because means our local like approximation is not so bad. Yeah, and this is our final result. Like still we train our neural networks and see the loss getting down. And finally we see all the spectrum. And the black one is the spectrum we know theoretically. And the blue one is all still the signal we can get from the quantum computer. And after using those data to train our neural network and do a long-term prediction, we can find we really predict the mass of the let's say the field, the Hamiltonian, much better than the raw signal. Uh, yeah, I think that's the key points to my talk. Any question up to here? Uh,
Thank you so much. I
eh,
want to open up the floor to any questions, both in the chat or if anyone would like to just unmute themselves. Perhaps there's some people in the room at SFU. Please go ahead.
yeah, if not, I can also show some other points. Like previously, I just show like how can we do the study on the neural operator. And here we want to know, I want to show like how can we really do that on the quantum computer? Like how do we really get the information from measurements? Uh, like for like as I said, for any coefficients we want to get, it's like doing trace on the operator in a chosen basis, and and we write it in this form, and this form is exactly the same when we do a measurement on a specific state called sigma I. Even sometimes this sigma I is impossible to directly build up, we can still build a state as a sum of different physical possible states, just do multiple measurement and sum them together. So we get all the coefficients depends on time, and we can then train any operators with such coefficient status. And also for usually for the different kind of theory, let's say different kind of Hamiltonian, uh, the operators usually have some symmetry. means the complete basis are, I mean, the full basis with 4 to n poly operators are more than enough. We can use those symmetry to reduce some of them. For example, I here show in such operators, we can prove some of the coefficients should be exactly 0. So we don't need to like use all the bases. We just need to pick out some of them, and that's already enough. As you see, like we insert sigma I to uh I guess I already specify I in sigma I in a special form. Uh Yeah, maybe I forgot right here, but yeah, anyway, I just want to show some of the sigma I should be there here. Yeah, here I wrote here the sigma I that anti-commute with the operator O. Like if those are anti-commutes, so it should be restrictedly become 0. And also, I want to point out a bit about more theoretical thing, like uh, to what we did is like for to learn a long-term behavior of a system, usually which is not linear and usually cannot directly solved. It's more like we want to solve some non-perturbative information from perturbative method, and this very close to very theoretical possible very theoretical thing called resurgence. Like it's also like we want to get some perturbative information from mm, sorry, opposite. We want to get some non-perturbative information from perturbative information because in it's actually thought in the quantum computer, like for such perturbative evolution is like it's like the state spare in the qubit state step by step. Means like if we usually have if we only have like very limited steps, yeah, the very long distance qubit are not going to be affected. So that's a bit strange, but also we know on the mathematical I mean on the expansion side, we know the such approximation is good enough. So it should be something like resurgence that we can learn the non-perturbative information from just the discrete the evolution operator and get signals. Yes, I think I finished all the topics. So, is there any questions?
Question here. Hi, thanks for the talk. As a few, I have a question.
Yeah.
So can you remind me, in your scheme, the role of a quantum computer is to generate those training sets, and then you feed into a classical neural network. Is that what the classical quantum computer is doing?
Yeah. It's like in quantum computer, we can get some sequential data, but those data are very limited. I mean, we can only have a short range data. We cannot do long-term prediction because the signal will be lost. And what we're using is like how can we utilize those short-term data? Like we can do very good prediction on quantum computer for any coefficients and use those coefficients to do long-term prediction.
So I'm wondering because at the end of the day you truncate the number of operators in your correlation function. So
Yeah.
that give me the impression that you are considering something that has a short-term correlate, so limited length correlation. So in that regime, will it be possible that there's actually some classical algorithm like matrix product say that can already describe the state pretty precisely, so therefore you don't even need a quantum computer? I'm just wondering. So whether what's the advantage of your
Well,
scheme
I think it's difficult because like for our truncation, we just not focusing on the full poly basis. We just focus on a subset of that. But such a subset is still a quantum measurement. It's a thing we have to measure really. I mean, for given a Hamiltonian retinal circuit and evolve operator and really run that thing on the quantum computer and do the measurement. And those counts are the coefficients we are considering.
Yeah, but you are neglecting those coefficients that have a chain of Pauli operators that is long
Yeah,
range interaction, right? Or long range correlation, right?
yeah, we neglect that.
Yeah. So therefore, if you are focusing on, hey, I already imply my system has only short range interaction, would it be possible to have some classical description of the state already?
I think that the point is if we can get a analytical solution of that short range poly operators. I mean, if not, we can only do on quantum on computer.
Okay.
Mm.
So and then do you study if you have some system like when you talk about those phase transition system? I suppose the phase transition system actually have long-term correlation. Have you tried different cases that some of them is more accurate than the other? What and use that?
For that we don't because like here we just want to make one more step, make it scalable, but we didn't do more than that. We do want to use that in different system, but at this point we just only consider the transverse Ising model.
Okay.
Mm.
Thank you.
Thank you.
Do we have any other questions? They can be put in the chat, or anyone else want to unmute themselves? Okay, if there are no more questions, I'd like to thank you on behalf of Quantum BC for your excellent seminar today, Jinyang. And I'd like to
Yeah,
thank
thank you so much.
everyone who joined us. Thank you so
Thank you.
much.
Yeah, thank you so much. So I stop sharing.